Okay, next up is Justin Wippo. Justin is a process engineer at Thermal Process Systems, where he has taken on the lead role in researching several new technologies the company he is developing. After graduating from Purdue University with a BS in chemical engineering, he passed his FE exam and was certified as an EIT, and is actively working towards his PE. Please welcome Justin.
Good afternoon, everybody. Thank you for sticking around to hear my spiel this afternoon, so I will get it going. So I'm going to be talking about our new technologies, primarily the targeted phosphorus recovery. Just use buttons. So to start, I got to take a step back and talk about when I came into the company and started with a new research project that led to what has become the targeted phosphorus recovery, and then looking at how we use nature to complement itself. So when I started with thermal process systems, I began our new research. If you know anything about TPS, it's an aerobic digestion company. So when I came in, I started researching our stab at combining anaerobic and aerobic digestion, with the overall goals of this to effectively combine anaerobic and aerobic digestion by creating optimal environments for the different bacterial cultures that we're employing. And we wanted to implement process control parameters that aren't typically there in most anaerobic processes, while decreasing the overall HRT and maintaining higher or improving the volatile solids reduction and biogas production. We also sought to establish a method to control struvite and H2S production in the anaerobic digester. So here you can see just the overall flow schematic. We went with a multi-stage or multi-phase anaerobic digestion process where we have a short HRT for VFA production and then a longer HRT tank for the conversion into methane. And that goes to our aerobic digester, which is our sweet gas reactor, or SGR. And our control parameter here is our recycle stream going from the SGR back to that acid phase. So skipping some of the results with the short time frame here, some of the most impressive results that we got from this were our dewatering results. Coming out of that last aerobic reactor, we had Centrisis do some centrifuge lab testing for us, and the results they came back with were that there was no required coagulant dosing and a very low polymer dose of only 18 pounds per dry ton of solids to dewater, and we achieved a 32% cake solids there. So as we saw, and the system also achieved 64% VS destruction throughout all three digesters. So looking at this high solids reduction and high cake solids, we saw that one of the biggest benefits of this system were the considerable decrease in the amount of material for a facility to haul away after it's all been processed. So we started looking at how can we further improve the dewatering portion, which led to our targeted phosphorus recovery, which started out as researching new methods for dewatering and became our new approach to phosphorus management. So we determined that all of this begins with digestion and having proper solids conditioning, and we address multiple issues that negatively affect dewatering, especially at B&R facilities or any facility that has a high amount of phosphorus, while we reduce chemical costs and give the client a potential to form a phosphorus product. Currently, when we look at managing phosphorus in wastewater facilities, many plants do this by their metal salt coagulants such as ferric and alum, where they form a metal phosphate precipitate that drops into the cake. However, as facilities start to reach higher and higher levels of phosphorus in their material, that's requiring more of these expensive chemicals, and then there becomes a balance point between treating the phosphorus and optimizing your dewaterability. And phosphorus recovery technologies typically target either struvite or brushite formation. However, many of these are often done as a pre-treatment or intermediary step, where they still have the solid material and other compounds that compete and can inhibit the efficiency. So looking at the basic steps of our new approach, beginning with solids conditioning either in our classic SNDR or this new SGR that I mentioned, going to dewatering, and then you have a phosphorus lean biosolid cake coming out and a phosphorus rich filtrate or centrate that you can form into your phosphorus product. Both the SNDR and SGR were originally developed for ammonia removal, but they're also efficient at removing soluble COD, VFAs, proteins, and carbohydrates, which are going to break up any EPS formation with that recycle, being that proteins and carbohydrates are some of the primary macromolecules that make up EPS. And through our nitrification cycles, we reduce the alkalinity, and these tanks are effective when following either an ATAD or an anaerobic digester. So looking at the SGR following anaerobic digestion, you saw that we didn't see any requirement for a coagulant while dewatering and a very low polymer dose. And kind of a similar trend with an SNDR following an ATAD, we have a reduction in the polymer consumption needed. However, because an ATAD and the thermophilic conditions that it has produces such a strong emulsion, there is still a need for a coagulant to break up that emulsion due to the cell lyse in that thermophilic environment. So we looked at replacing a standard coagulant with vitriol. When you look at that in comparison to either ferric sulfate or aluminum sulfate, they're almost identical compounds without the heavy metal that's going to form your phosphorus precipitate. So using this gives us some additional hydrolysis that's going to rupture cells and release stored polyphosphate. It's going to lower the pH to either solubilize precipitates that have formed or to help keep magnesium and calcium soluble through the dewatering process. So it's going to lower your monovalent divalent ratio, which will improve your dewatering capabilities. And with lower alkalinity means that you have less chemicals required. So the SGR or SNDR are going to be keys here. When we dewater, we ensure that the pH is at a safe level for the dewatering equipment. Like I mentioned, the smaller hydrogen ions are going to coagulate the biosolids through the same charge neutralization mechanism as your ferric or alum would, but you're not forming these heavy precipitates that are dropping into the cake, and because they're large compounds, they leave additional interstitial space for water to be stored too. So we have less material to bind, which leads to less polymer required to dewater. And we also have seen, since we're not dropping all this phosphorus into the cake and keeping it soluble through dewatering, this brings the cake N to P ratio more in balance. Lab testing shows over a 30% decrease in the mass of the cake produced, while centrifuge testing shows over 35% cake solids being achieved. And right here, looking at the TPR method of dewatering versus the ferric, there's a noticeable size difference right off the bat. So we have this phosphorus-rich filtrate that comes out after the phosphorus lean biosolids. And this filtrate or centrate is going to have minimal alkalinity and biological activity remaining. So with the absence of solids and other compounds in the material, that's removing the contaminants that are going to lower your phosphorus recovery efficiency seen in other technologies. That leftmost picture there is about 10 seconds after only a pH adjustment. I believe these are struvite here. But so with just a pH adjustment, not even a magnesium dose, we precipitated out about 80% of the phosphorus. Looking at our averages, we could keep about 83% of the total phosphorus soluble while precipitating 92% of that. So this allows us to remove just under 80% of the total phosphorus in the material. Now, when we look at what we believe are ideal TPR systems, beginning with enhanced BNR, going either on the left side with the anair system of an acid phase digester, anaerobic digester, and the SGR, then we go to TPR dewatering, where you have your phosphorus lean cake coming out, your phosphorus rich filtrate you form your phosphorus product with, and then you have a low phosphorus return back to the head of the plant. With an ATAD SNDR system, it's essentially the same way. You just have that additional need for some coagulation through the dewatering step. Switching back to our anair pilot and how it's operating currently, we began operating with a 60% recycle going from the SGR back to the first tank, and then we bumped that way up to 200% as we were starting to look at the effects of decreasing the ammonia in the anaerobic digester to move us out of the struvite precipitation potential. And with that, we decreased the ammonia in the anaerobic digester from 1,500 to 500 milligrams per liter, and maintaining less ammonia and ammonium in the anaerobic digester also lowered our pH in the tank from 7.2 to about 6.7. And throughout this, we maintained consistent VS destruction and biogas production. And looking at the combined effects of the lowering ammonia and lowering the pH, I know this chart's a little bit small, but so we started, this is a struvite precipitation potential tool from Sacramento State University, starting at the conditions that we were at, 1,500 milligrams per liter of ammonia, a pH of 7.2, and the material that we use for the pilot doesn't have a lot of phosphorus, so I used an arbitrary higher number. With 1,000 cubic meters per day of that flow rate, you're producing about 440 kilograms per day. And as we step that down to where we're at now with 500 milligrams per liter and a pH of 6.7, theoretically there is no struvite being formed at all. And also with this increased recycle rate, testing showed that we had a total elimination of H2S in the biogas, or at least non-detect, under 1 part per million for the Draeger tubes that we're using to test it. In looking through research to better explain this, we saw research dating back to the 80s that supplying nitrates to the acid phase, so supplying nitrates to this anaerobic environment, is going to inhibit the activity of sulfate-reducing bacteria, and it actually promotes the activity of a different sulfur-oxidizing nitrate-reducing bacteria. So at the same time, we're both reducing the potential for H2S to form in the anaerobic digester while carrying out our denitrification step. So rather than our SNDR, where we have to cycle between aerobic and anoxic states to remove the nitrogen, we're only nitrifying in that last tank and then denitrifying in the first tank. So that's where part of the complements, as we see, we're using these known biological processes to complement each other. So not having any H2S in your anaerobic digester is going to eliminate the need for an iron sponge or any iron dosing to control it. So when we look at one of these complementary systems, looking at the anair process, you start with your denitrification acid phase digester. You can go to any number of methanogen reactors or the larger anaerobic digesters. Then we go to the SNDR reactor. So there's the recycle going back through a heat exchanger to reclaim some of that heat with the fresh material going into that first digester. We'll come out of the SGR, only adding polymer, dewater for a high solids, low phosphorus Class B cake, and a phosphorus-rich centrate that you can, depending on what the client wants, can use any number of technologies with a higher efficiency to recover that phosphorus as a product. And then you have your low phosphorus return back to the head of the plant. So what we've seen in some facilities, especially B&R facilities that don't properly address phosphorus in their dewatering steps, are that they'll begin to cycle up, where they have a small recycle going back at first, and then that just builds and builds and builds. We've seen some to the point where the PAOs in their B&R system essentially can't keep up with it, and then they start not meeting their effluent phosphorus limits. So being able to keep the phosphorus soluble through the whole digestion process and then recovering it after the dewatering in a much simpler form is going to lower the phosphorus return to the headworks and begin to cycle down that plant. Combine that with the lower ammonium pH in the anaerobic digester, you're going to significantly reduce the potential for any struvite to be forming. And with the SNDR after an ATAD, you're going to see the same cycling down effect. So in summary, conditioning material is critical to provide a cleaner chemistry for the targeted phosphorus recovery. We target the phosphorus to remain soluble through digestion and through dewatering. We remove expensive standard coagulants. We improve the dewaterability of biosolids and leave multiple routes for recovering the phosphorus after dewatering. The ANAIR pilot study showed that we can effectively implement process control parameters in anaerobic digestion. We demonstrated a significant reduction in the material to haul after the process. We reduced the precipitation potential in the anaerobic digester and eliminate H2S in the biogas. And then the ANAIR with the TPR is a solution for many of the issues typical of anaerobic digestion processes and an innovative use of tried and true science and technologies, which we believe really creates the complete package. So as we look ahead, both of these technologies are patent pending right now, and we're currently looking for a facility to install and operate on-site pilots as a further proof of concept on somebody else's material. Thank you. Questions? Yes?
At the end of the day, I think I followed along okay. The SGR is an aerobic reactor that's nitrophile without denitrophile.
Correct.
What kind of SRTs are you targeting for that?
Right now, with the pilot, we're running it at 4 days, and it seems to be doing quite well. So the overall HRT for the process right now is 20 days.
And you're not getting Class A out of that?
Correct.
You are or not?
We are not. Yes?
Yeah, I'm a bit we're trying to figure out. I think the SMDR and the NAR were previously far before the pad was patented. I'm looking at the history of the technology. So how do you have issues now with TPS in terms of selling this product? Because Wippo, for example, was able to basically license the patent, at least one patent for the pad process. And in fact, what differentiates your process, with the audio type, from the pad process that is currently out there, which is more developed?
Well, the main thing with the differentiation there is both the separation of the nitrification and denitrification steps, and then also its ability to control other aspects of the anaerobic process, like the H2S production and lowering the struvite potential.
Now, I understand that in the anaerobic production, talking about the aerobic that is after the anaerobic. That's what I had in the anaerobic production. Because you basically are practicing cycling anaerobic, anaerobic.
Right, I guess it's kind of a different approach to a pad, you could say almost.
I'm just curious, I just have no idea how they able to patent that process. Because you have facilities that have been for like decades in the TPS that's operating after a pad.
Mm-hmm.
And pad has did it all. For some reason, this process is just something I think about.
Well, we'll see if it gets approved. Yes?
Yeah, the concept here was coupling with acid-phase digestion. If, looking at a facility that wasn't interested in acid-phase digestion, but was interested in the downstream, was something that could be, another configuration without acid-phase.
For the TPR dewatering or with the SGR you're talking?
Talking about, sorry, I'm getting confused with acronyms, but thinking
Right.
with the aerobic after anaerobic digester with dewatering, if it wasn't having, there's only so many plants that have acid-phase digestion.
Right, and I think, I don't think that we're confident that it would work as well in being that, because something that's come up before is that recycling those nitrates back to the acid phase, in fact, makes it an anoxic tank, but because we denitrify completely, acidogens are facultative anaerobes, so they can function in an anoxic state, whereas methanogens are true anaerobes. So I don't think, that's where I've seen issues with other processes, that recycling a nitrate heavy stream straight to an anaerobic digester, I don't think will have as good of performance as what we see. Anybody else? Thank you.
We're on the verge of party time. Okay, we have a reception for you out there. Kathy Ravelay, my admin person, has drink tickets. You each get one. Oh, she's there, right there. Okay, so as you leave, be gentle with her. I know you'll be very anxious, but she has only one hand and it's good. So thank you very much for the great day and all the speakers, and thank you to the moderators, Micah and Christina, and we'll see you tomorrow.
Recording.